All right, my children, now we are going to talk about percent yield, or how to herd cats. This idea of herding cats is an analogy that I'm going to be making to help you think about what we're really talking about. So herding cats is like a phrase, like it's as easy as herding cats, which is like a joke because it would be really hard to herd cats. Like they don't go where you want them to, because like the entire nature of cats is like, I do what I want, right? So they're not gonna like listen to you the way that like cattle would when you're trying to herd the herd of animals. And that's sort of like where this analogy starts. So just kind of keep that in mind. When we do stoichiometry, that is always based on an ideal reaction in a perfect world. A lot of reactions do not go to completion, which is what it's called, like where not every reactant turns into a product. Like you don't always get what you expect to get. And so our real life analogy example is herding cats. Let's say that Miss Lestick, who is another one of the chemistry teachers, is trying to herd 200 cats from her home in Austin all the way up I-35 to Round Rock High School. In theory, in a perfect world, how many cats should make it all the way to Round Rock High School? Well, if it was a perfect sunshine and rainbows kind of world, then all 200 cats would make it. 200 cats is what's called your theoretical yield. Your theoretically, if it was a perfect world, how many cats would make that? I'm going to generally refer to that as TY because I'm too lazy to write all of that every single time we need to talk about it. So that's my abbreviation, TY, theoretical yield, the perfect sunshine and rainbows world version. But in the actual world, how many cats would make it? Well, in the real world, some cats are going to get distracted. They're going to climb trees and chase mice and squirrels. And maybe horrible things will happen to them that we're not going to think about. But cats are going to escape in the real world. Not all 200 cats are going to make it to Round Rock High School. So maybe only 189 cats make it. That would be called your actual yield, your actual real world sad rain cloud yield. Like the amount you actually get. Please also remember, as we're talking about this, the yield is like the definition of the word yield here. We're not talking about like in driving where it means like let other people take their turn first. That's not what yield means here. We're using the word yield the same way you would use it in a recipe. Like if I say this recipe yields 24 cupcakes, that means it makes 24 cupcakes. So we're talking about yield in the sense of like how much stuff is made. So just keep that in mind also. So your actual yield, or again, I'm going to have an abbrev for this, AY. Your actual yield, how much is actually made, maybe only 189 cats make it. Your percent yield is a ratio of what you actually get compared to what you theoretically should get if it were a perfect sunshine and rainbows world. So there's actually a formula for this. Your percent yield is the actual yield, AY, divided by the theoretical yield, TY, and then the whole thing times 100. So you take that sad rain cloud number on top, divided by the sunshine and rainbows number on bottom, times 100, and then you get your percentage. So 189 out of 200 times 100, 94.5% of the cats made it in that first example. Let's say once those 189 cats get to Round Rock High School, the rest of the chemistry team takes 75 of those cats and we try to herd them down to Mr. Groff's office to give him a nice surprise. But only 73 cats make it from the 600 building down to Mr. Groff's office. Because again, it's like a big campus. We got to go outside. We're not going to get all 75 of those cats through the like outdoors, all the way down the main hallway, all the way into the office. It's just not going to happen. So maybe 2 of those cats run off. What is our percent yield there? Well, the 75 cats, that's our sunshine and rainbows number. And the 73 cats, that's our sad rain cloud number. Oh, it's so sad. And we're going to take that actual yield of the 73. We're going to divide it by the theoretical yield of the 75, still times 100, because that's going to turn like our decimal into a percent. And 73 divided by 75, whoops, I typoed, is 97.3%. 0.33, because we're going to round to the hundredths place always. Okay. Just like cats, not all atoms from the start make it to the end of a reaction. Not every reactant turns into a product. Sometimes stuff like gets stuck to your beaker, or maybe it didn't dissolve all the way, or like all kinds of stuff can happen. Maybe it wasn't warm enough for all of it to dissolve or react, or like whatever. Not everything's going to become a product. To find that perfect theoretical yield, we're going to need stoichiometry. Woohoo! Mole bridges. You're going to start with a given reactant and draw a mole bridge to the product. So like they're going to give you like some reactant, and you have to draw a mole bridge over to whatever product they're asking for. And then what you get from that would be your theoretical yield. In an actual lab, not everything's going to 100% become a product. So to find the actual yield, you want the amount that was actually produced in the lab. They will have to give that to you. It will be a given product, okay? It will be a given product. So like they will give you some reactant. You have to follow a mole bridge to turn it into a product. And then they will also give you some product, and that given product is your actual yield. And then once you find your actual yield and your theoretical yield, you just divide them times 100 to get your percent. Easy. Again, please note the word yield here means made or produced. So the yield has to be a product, because that's literally what the word means. You're going to be looking for a product that was yielded. Okay, let's try an example. Let's calculate the percent yield for a reaction if 53.4 grams of K2O react to produce 32.7 grams of K3N. I highly recommend that you take like whatever numbers are given to you and you like write them into the reaction, so you can like very obviously see what's your reactant and what's your product. So one given, notice there are two givens here, y'all. A given and another given. These are G's. They don't really look like G's, but we can pretend. Okay. 53.4 grams of K2O. So that's this one. And 32.7 grams of K2 or K3N. That's this one. Okay. We have two givens. One of them is a reactant and one of them is a product. The given reactant, we're going to have to use a mole bridge with. The given product just is our actual yield. So if we take a look, this given product right here, that's my actual yield. I already have that actual yield. So like down at the end of this problem, when I'm calculating the percent yield, the actual yield I already have. They've already given it to me. It's that 32.7 grams of K3N. It's going to be over something times 100 to get my final percent. But they've already given that to me. I already know where that number is going. But that 53.4, we have to actually do something with. We're going to have to follow a mole bridge with it. So here we go. We're going to start with that 53.4 grams of K2O. Oops. Okay, and we're going to have to find grams of our product because that's like when we do the final formula, whatever, if we're going to get grams to simplify out, we're going to have to divide by grams divided by grams so that you have the same thing on top and bottom and they simplify out, and then you're only left with like this percent sign right here is your final unit, so that your final answer can also be a percent. So we know we're going to have to end with grams of the product here. as our like final answer to this, which means if we're going from grams to grams in this mole bridge, we're gonna need 3 fractions. This is a 3-step problem. Draw your fractions. There's a couple things we do at the start of every stoichiometry problem, like easy steps, always the same steps every time. So start with your given, check, done. Okay, your unknown goes on top at the end. Check, done. What goes up must come down. Check, done. And then figure out where your mole bridge is going to go. You know that the mole bridge can only have moles on it, which means there's only one fraction where you can put the mole bridge here, because it cannot go on this first fraction because there are grams in that first fraction and it's a mole bridge. It's not a freaking gram bridge, okay? So it can't go there. It can't go on the final fraction because, again, there's grams on that fraction and it's not a freaking gram bridge. It's a mole bridge. So you cannot put the mole bridge on a fraction that has grams. That means the only place your mole bridge can go is on that middle fraction. And remember, your mole bridge always goes from your given into the unknown. You thought I was done singing that, didn't you? I'm not. I will never be done singing it. Into the unknown. Remember, oh, shoot. I just scrolled by accident. Bloop, bloop, bloop. Okay. Remember, your given should always be the bottom of your mole bridge fraction, into the unknown on top of the mole bridge fraction. So that means our given, right, was K2O. Our unknown is the K3N, and it's a mole bridge. So those need to be moles in both of those places there. Mole, because it's not a freaking gram bridge. It's a mole bridge. In your mole bridge, remember your numbers that go in your mole bridge are the coefficients of the reaction. Those coefficients from the reaction are what should be going into your mole bridge fraction every time. So your given was 3 moles of K2O. Your unknown is 2 moles of K3N into the unknown. Use those coefficients in your fraction for your mole bridge. Then we got to fill in these last couple spots. What goes up must come down comes into play again. So these moles of K3N, what goes up must come down. Moles of K3N must be over here. And then similarly, what goes up must come down. So if moles of K2O came down to the bottom of that middle fraction, then moles of K2O need to be on top of that first fraction. So now we've got 53.4 grams of K2O times, and our first fraction is some number of moles of K2O divided by some number of grams of K2O. Well, this is a conversion that goes back to like kicking it old school, where before we did stoichiometry, our number of moles in a fraction was always just 1. So we're going to put 1 mole of K2O on top of that fraction. And then on bottom, our number of grams needs to come from the periodic table. So grams of K2O from the periodic table, that means we're going to have to add up 2 potassiums, which on the periodic table, potassium has a mass of 39.10. And then 1 oxygen, which is, again, on the periodic table, 16. If you add all of that together, 2 times 39.10 plus 16 is 94.2. So that is our number of grams for K2O. And then for our second fraction, we had our mole bridge. So the given on the bottom of the fraction was 3 moles of K2O, where that 3 was our coefficient from the reaction. The unknown on top into the unknown on top was 2 moles of K3N. Again, the 2 coming from the coefficient in the reaction. And then our third and final fraction here is grams of K3N over moles of K3N. This, again, is a kicking it old school style fraction where you're using just 1 as your number of moles. So the number of moles on bottom there is just 1 mole of K3N. And your grams, again, need to come from the periodic table. So K is 39.10, and this time there are 3 of them. And then nitrogen is 1 times 14.01. And again, when you add all of that up, 3 times 39.10 plus 14.01 is 131.31. And that's your number of grams of K3N that go on top. Now we just got to like multiply the whole thing, right? So top times top times top times top divided by everything on the bottom. You don't have to put a times 1 into your calculator or a divided by 1 into a calculator. You know that's not going to change your value at all. So what we end up doing here is 53.4 on top times that 2 that's on top times 131.31 that's on top, divide by 94.2 because it's on bottom, divide by the 3 that's on bottom. And you should end up with 49.62 if you put it in your calculator correctly. Ta-da! That number that we just found is our theoretical yield. That's our theoretical yield. So you theoretically could, if everything went perfectly, make 49.62 grams of this product K3N. And that theoretical yield should be going on bottom of your fraction for your formula for percent yield. So remember, coming back around, we were given an actual yield at the beginning of the problem, 32.7 grams of K3N. That's how much was actually made. Theoretically, we should be able to make 49.62 grams if everything goes perfectly. We did not get everything to go perfectly. We were only able to make 32.7. So now we're going to use that formula, actual yield, 32.7, over theoretical yield, which is 49.62, the number we just found, times 100, and it comes out to 65.90% for our yield. 65% is not a good yield, by the way. That's okay. We'll try again next time in the lab, I guess. I mean, this is all just the math version anyway. But I mean, you get me. You probably get me. You probably don't get me. It's fine. You can just watch the video again or something. It'll be fine. Anyway, that's percent yield.